All right, today we're going to dive into a piece of tech that's, well, it's kind of everywhere, but you almost never actually see it. We're talking about the invisible workhorse of our modern world, the heat exchanger.
So, to get us started, let me ask you a quick question. What on earth could your car, the fridge in your kitchen, and a massive power plant possibly have in common? I mean, they seem like they're from completely different worlds, right? But here's the thing, they all depend on the exact same kind of device to work.
And that device is the heat exchanger. It's this unsung hero, this invisible workhorse, quietly working behind the scenes to make so much of our daily lives possible. So today, we're going to pull back the curtain and see exactly how it gets the job done.
Okay, so here's what we're going to cover. First, we'll define this invisible workhorse. Then we'll get into the golden rule of heat that makes it all possible. We'll check out the two big families, direct versus indirect transfer, and meet a key player called the recuperator. After that, we'll see how just changing the direction of flow is a total game changer, and then we'll wrap it all up.
All right, first things first. What in the world is a heat exchanger anyway? You know, when you get right down to it, the idea is incredibly simple. A heat exchanger is basically just a gadget that moves heat from something hot to something colder. Its job could be heating something up, cooling it down, evaporation, condensation. It's all about controlling the transfer of heat.
And believe me, these things are everywhere. We're talking massive power plants, chemical factories, the food industry. Heck, there's one inside your computer right now keeping it from melting down. And yeah, of course, the classic car radiator. They really are the unsung heroes of modern engineering.
So how does it all actually work? Well, it's not magic, it's physics. And it all boils down to one super simple universal law. Let's call it the golden rule.
Here's the deal. The second law of thermodynamics. Sounds complicated, I know, but it's not. It just says that heat will always move from a warmer place to a cooler place. Period. No exceptions. Heat exchangers don't fight this rule. No way. They're built specifically to harness it and make that natural flow do useful work for us. Now, even though there are tons of different designs, they pretty much all fall into one of two big families. And it all comes down to one simple question. Do the hot and cold things actually touch? First up, you have direct transfer. It's exactly what it sounds like. The two things, say hot water and cool air, literally come into contact and mix together. A giant cooling tower is a perfect example. But then you have indirect transfer. Here, the two things are kept totally separate by a wall. They never, ever mix. All the heat has to travel through that barrier. Your car radiator, a classic example. The hot coolant stays in the tubes while the air flows past on the outside.
So for the rest of this, we're going to focus on that second type, the indirect exchangers, because honestly, that's where you find the most common designs. So let's meet the real workhorses of the family, the recuperators.
Recuperators are your classic indirect exchangers. The key idea here is that the hot fluid and the cold fluid are flowing through the device at the exact same time, but they're always kept separate by a wall. This means you get a continuous, steady transfer of heat happening in real time.
So how does the heat actually jump across that wall? Well, it's like a little three-step dance. Step 1, convection. The heat moves from the hot fluid to the wall. Step 2, conduction. The heat then travels through the material of the wall itself. And step 3, convection again. The heat moves from the wall into the cold fluid. So, hot to wall, through the wall, and wall to cold. Simple as that.
And engineers have come up with a bunch of ways to build these things. You've got tubular types, which are simple and awesome for high pressures. There's shell and tube, which is the go-to for condensing steam. And then there are plate exchangers, which are super compact and efficient, perfect for when you don't have a huge temperature difference to work with. The point is, you pick the right tool for the specific job.
Okay, so you've got two fluids, a wall between them. Sounds straightforward, but here's where things get really, really clever. It turns out that the direction those fluids are flowing makes a massive difference in how well the whole thing works.
First, we've got parallel flow. This is the most obvious way to do it, right? The hot fluid and the cold fluid both enter at the same end and travel in the same direction, side by side, like two cars on a one-way street.
But here's the catch with parallel flow. Because they're flowing together, the cold fluid can never get hotter than the hot fluid is when it leaves. They just sort of approach a middle temperature together. It works, for sure, but it's not the most efficient way to do things.
Now let's flip it around with counterflow. This time, the fluids enter at opposite ends and travel in opposite directions, passing each other along the way.
And this is where the magic happens. It's actually mind-blowing. In a well-designed counterflow system, the cold fluid is at its hottest right as it's leaving. and at that very moment, it's passing by the hot fluid that's just entering at its hottest. The result is just incredible. The cold fluid can actually leave the exchanger at a temperature that's hotter than the hot fluid's exit temperature. This is a massive deal for efficiency. It means you can recover way more heat and save a ton of energy.
And finally, there's crossflow. In this setup, the two fluids flow at an angle to each other, usually 90 degrees. Just picture air flowing across the fins of a radiator. That's a perfect example.
So why bother with this one? Well, crossflow gives you really precise temperature control, which is super important if you're working with something that's heat sensitive. You'll also see it mixed and matched with the other flow types to create highly specialized hybrid designs.
So let's bring it all together. What's the big picture here? We've seen how this seemingly simple device, just by following a basic law of physics, acts as this quiet but powerful engine driving efficiency all around us.
So if you're going to remember anything, remember this. 1. Heat exchangers are everywhere, and they just move heat from hot to cold. 2. They're either direct, where things mix, or indirect, where they're kept separate. 3. Recuperators are a huge group of those indirect types. And 4, and this is the big one, when you want maximum efficiency, counterflow is king.
And that leaves us with a final thought. In a world that's constantly demanding better energy efficiency, in our homes, our cars, our industries, this humble heat exchanger is more important than ever. So the real question is, what new innovations will this invisible workhorse make possible next? Thanks for watching.